In this next section, we will be considering the various parameters that bring about a good GC experiment. By good, I mean that we should have peaks that are well resolved, allowing us to identify and quantify, and also allowing us to perform the analysis in the shortest possible time. So a few of the criteria that we'll be thinking about is the split ratio for the injector, the carrier gas flow rate, and this third one we'll really focus on, that would be the temperature selection. Do recall that the column sits in an oven, which is a temperature controlled environment, and the temperature directly affects the rate of elution of various chemical components. So that is going to directly affect the resolution that we observe. And these were some of the column parameters that we also talked about: the size of the column, length of the column, film thickness, and things like that. So the key issue we want to talk about here is the effect of temperature on elution rate. So the thing we must remember is that when we have a high column temperature, the peaks are going to elute faster. If we have a high column temperature, the various chemical components will not be interacting with the stationary phase as much, so you'll just be interacting very little, and this will lead to generally faster elution for all the components. The opposite is also true. If we have a low column temperature, then the extent of interaction with the stationary phase for all the chemical components is going to be quite high. So they're going to spend quite a lot of time interacting with the stationary phase, but will therefore take a very long time to elute from the column. So this is a situation where there isn't a perfect temperature. High column temperatures lead to shorter analysis time because everybody is eluting faster, but we get generally less retention, so therefore less separation. If we switch over to a low temperature, then we will get very good separation because generally all the chemical components are interacting well with the stationary phase, but it will be very slow. The overall analysis will take an extremely long amount of time. So what we are actually aiming for when we select temperature are three things. The first is well-resolved peaks. This is a given. We must have at least 1.2, if not 1.5 of resolution in order for our peaks to be considered well separated from each other. Only then can we perform analysis and say that we can identify and quantify these chemical compounds. What we would also like is a short analysis time. So earlier we mentioned that if we are doing 10, 20, maybe 30 analyses, we do not want to be in the lab for an extremely long period of time, so it would be best if each of our analysis is as fast as possible. Of course, we want to select conditions that will allow us to get narrow peaks, because narrow peaks will eventually lead us to good resolution and therefore improve our chances of separation and having an accurate analysis. So I want to talk about this idea of column temperature programming. Earlier we talked about how both having a low temperature and a high temperature have its own issues. So a low temperature will lead to a very long analysis time, while a high temperature will lead to insufficient interaction of the chemical components with the stationary phase, and is likely to lead to insufficient separation. So it turns out that for a GC instrument, it allows us to change the column temperature at different points of the analysis. What that means is that we can typically start off with a lower temperature. So this will allow compounds with low retention by nature to spend a bit more time interacting with the stationary phase, and therefore leading to well separated and well resolved peaks. Then at a later point in time during the analysis, we can quickly raise the temperature of the column so that compounds that are high retention by nature can be essentially chased out of the column, so they elute a lot quicker, and we can also obtain sharp and well-resolved peaks for these compounds. So actually, using column temperature programming, we can get the best of both worlds. We can start off with lower temperatures for compounds that by nature are not very well retained, and then at a later point in the analysis, we can raise the temperature to chase out the compounds that by nature are very well retained. So this is an example of a temperature programming sequence, whereby we may start off the instrument at 120 degrees Celsius, which is considered quite low, and we can keep it there for 2 minutes. This allows 2 minutes of time for the lowly retained compounds to interact with the stationary phase. And then at this point, we may want to raise the temperature by 10 degrees per minute to 150 degrees C. So 150 degrees C is sort of a mid-range temperature, and we can hold it there for say 5 minutes to allow the medium retained compounds to have some opportunity to interact with the stationary phase and therefore be separated. And then now that we are much later in the analysis, we can quickly raise the temperature 30 degrees per minute to quite a high temperature, so 270 degrees C. And at this high temperature, the very highly retained compounds will be essentially chased out of the column, right? So this ensures that the overall analysis time does not take too long. So the very highly retained compounds do not stay for too long in the column. Now, we have 3 chromatograms here, and these chromatograms will illustrate how temperature programming works. If we look at the chromatogram on the left, we can see that it is run at a fixed temperature of 45 degrees C. So this is actually a very low temperature. So what we see on the left-hand side of the chromatogram is that the peaks are reasonably well resolved. So these are the very lowly retained compounds that by nature do not interact much with the stationary phase. But at this low temperature, they are actually quite alright and quite well separated. But the problem is, if we run the experiment at this temperature, at this low temperature, even after 30 minutes, we only have 5 peaks that have eluted from the column. So it turns out that there are 4 more peaks that have not even come out from the column, right? So if we are to continue waiting for those 4 peaks to elute, it's going to take an extremely long amount of time. Now, if we look at the second chromatogram, we'll see that this is run at a reasonably high temperature of 145 degrees C. So the earlier problem of peaks not eluting, that doesn't happen, because you can see that even by 20 minutes, we already have most of the peaks out. But the problem is that on the left of the chromatogram, if you have all the lowly retained compounds eluting very quickly, then of course all of them are mashed together and not well separated. So you can see that there are a whole bunch of peaks, up to 6 peaks, mashed together at the front of the chromatogram. Therefore, it will be impossible to separate or to identify these peaks. So the key is that when we start off the chromatogram, we want to start off at a low temperature. So this will allow the compounds that are by nature not that well retained to give them an opportunity to slowly pass through the column and therefore interact with the column and generate separation. So this happens at low temperature. But towards the end of the analysis, we want to raise the temperature. You can see that we are raising it to 120, 150, 180. And when we raise the temperature, we'll allow the very well retained compounds to leave the column. So therefore, by 30 minutes, we have essentially all our 9 compounds out of the column, right? So we do not have to wait for a very extended period of time. So this is how temperature programming helps us. It allows us to start with a low temperature to separate the not retained compounds, and at the end it allows us to raise to a high temperature so that we can get all the highly retained compounds out of the column and towards the detector. Now, let's talk a little bit about qualitative analysis and quantitative analysis. The term qualitative analysis refers to the identification of chemical compounds. Now, in gas chromatography, we typically identify compounds based on their retention time, because we know that if I take a specific chemical component, let's say ethanol, and I put it through the instrument, and ethanol, say, has a retention time of 3.5 minutes, then I know that if ethanol is present in a given sample mixture, I should see a peak at 3.5 minutes. So therefore, using this concept of retention time, or by matching the retention times of particular chemical components, I can actually identify whether certain chemicals are present in certain samples. So this technique is actually used in a wide variety of applications. So you can see that in food, in fragrances, and also in various medicinal products. So the key is that under the same conditions, using the same instruments, the retention time of a identical compound will always be the same. If ethanol elutes at 3.5 minutes, then each and every time it will elute at 3.5 minutes. So using that property, I can therefore identify whether ethanol is present or not in any given sample. Now let's talk a little bit about quantitative analysis. Quantitative analysis is the process of figuring out how much of a particular chemical component is present in a sample. Now, GC is actually a very useful method for doing quantitative analysis, but I do want to highlight one key area of error that shows up and how to solve it. So when we do a gas chromatography quantitative analysis, we typically will take a small volume of sample, typically 1 microliter, and inject it into the instrument using a small syringe. So of course, when we do this injection, it is not physically possible to inject the identical amount, 1 microliter, each and every time, right? Sometimes I will inject a little bit more, and sometimes I will inject a little bit less. On top of that, because the sample injection pot on the instrument is heated, when I take the syringe and I am about to inject it, it's inevitable that a small amount of the sample may evaporate, because this is quite a volatile sample. So therefore, both of these factors will lead us to a variation in the actual volume that's injected into the instrument. So if the volume of sample injected into the instrument varies, from injection to injection, then the peak areas of various chemical components will also vary. So how do we correct for that? Alright, so this actually describes what I'm saying. If, for example, I inject 1 microliter, I expect a peak of a certain size, right? But if I accidentally inject a little bit less, so let's say 0.9 microliters, then I expect to see that peak of, let's say, ethanol to be somewhat smaller. And if in the third injection, I inject a little bit more, I expect the peak to be a little bit bigger. So therefore, if I plot a calibration curve of peak area against concentration, then actually it will not be accurate, because the peak area is varying not just based on the concentration, but it's also varying based on my fluctuation in injection volume. So the question is, how can I correct for that? I can correct for that using a method called the method of internal standards. The internal standard is a secondary compound that is deliberately added to the sample to produce a secondary peak. So for example, if I was analyzing ethanol, I would choose some similar but distinct compound, so let's say propanol as my internal standard, and I would add a fixed amount to each sample. How does that help me? Well, if we look at my first picture here, you see that in a 1 microliter injection, I have my ethanol peak, that's the black peak, having a certain size, and my propanol peak, the red peak, having a certain size. In the second injection, whereby I accidentally inject a little bit less, logically I would see that the size of both peaks, the ethanol peak and the propanol peak, they both decrease in size. In the third injection, whereby I accidentally inject a little bit more, then I will see that the ethanol peak and the propanol peak actually both increase in size. But the key is that throughout these 3 injections, the ratio between the size of these 2 peaks actually remains the same, because they both increase and decrease based on the injection volumes by the same relative amount. So if I can plot peak area ratio, so if I take the area of the black peak divided by the area of the red peak to get a peak area ratio, and I plot that against concentration, then that actually does not change despite the fluctuations in injection volumes. So therefore, on my y-axis of the calibration curve, I will plot the peak area ratio against concentration on the x-axis, and what I should observe is that I will get a reasonably linear line where despite the injection volume fluctuations, I can actually get very accurate results. So the method of internal standards is particularly applicable to gas chromatography, right? And I've described that we use a secondary compound that is deliberately added to the sample so as to correct for injection volume fluctuations. Now, there are many advantages of using gas chromatography as a method of analysis. Now, most gas chromatography experiments can be completed between 15 to 20 minutes, so that is a reasonably short analysis time, right? It also only requires a very small sample size. So you noted that our injection volumes are on the scale of 1 to 2 microliters, which is very little. So that's really helpful when we have only a limited amount of sample available for injection. The gas chromatography instrument is also able to separate very similar compounds that belong to the same family. So for example, if you have methanol, ethanol, and propanol, they're actually very similar compounds that belong to the alcohol family. But GC is able to distinctly separate these compounds based on the column used, and can give us very identifiable retention times for each of these 3 compounds. We also realized that the retention times can allow us to create a positive identification for each compound, because each time a specific chemical component passes through the instrument, it will elute with a very fixed retention time. So as we close this topic, I just want to highlight that there are actually very wide ranging applications for gas chromatography. So it's certainly not limited to to these three areas here: environmental, clinical, petrochem, food. It's certainly used in almost every industry you can think of, right? Because there are so many compounds that are suitable for gas chromatography, and also this instrument technique is actually quite an affordable technique for many companies to use. So again, I would recommend that there's no real need for us to memorize these applications, right? The point of this slide is that gas chromatography can be applied to a wide variety of applications across many different industries. So that brings us to the end of the gas chromatography topic, and hope it has been an enriching topic as we close.